Hello, my name is Frank McKenna. I'm here at UC Berkeley, working for the Near East Sim Center. In this video, I'm going to quickly talk about computers and computer programs to a depth that you're really going to need to understand to be effective C programmers. So what is a computer? A computer is a device that is programmable and it manipulates data. The data is in the form of zeros and ones, i.e. it's binary data, and the manipulation of that data is performed by the programs running on the hardware, telling the hardware what to do. Computers are great, but they're actually incredibly limited in what they can do. They're very stupid machines. They can compare digits. They can add, subtract, multiply, and divide numbers, whether those numbers are integers, floats, or doubles. But what they can do and why everybody uses them is because they do these operations incredibly fast. So how fast? What I'm showing in this slide is LINPACK results for the Intel CPUs running Intel MKL library. It's a nice benchmark for civil engineers, structural engineers, because LINPACK is basically solving the AX equals B matrix equation. And what they show is that on average, we can get 160 billion floating point operations per second. That is the performance we can get from our little laptop computers. If you want to put it in perspective, currently the world's population is about 8 billion people. So what this means is my computer in 1 second is performing 20 floating point operations per person per second. That's just an incredible amount of operations or performance we can get out of one of these little laptops we're using right now. So what is one of these computer applications? It's something that takes the binary input and produces binary output. For AX equals B, the binary input will just be A and B in binary form, and the output is just going to be a vector X, again in binary form. Internally, a computer program, it's basically a sequence of instructions. Each instruction is just an array of 0 and 1s. Each instruction does one simple task. For example, it might data value that's in RAM and bring it to the core, or it might take two numbers that exist in the core and multiply them. And then another instruction might be to take the result from that operation and put it into another register, or then take it from the register and put it back into main memory. 45 years ago or so, one of the original desktops that people could buy was this Altair 8800 computer. Each instruction had to be input. See these little knobs at the front? Each instruction was basically, each 0 and 1 was basically corresponds to one of these little switches. You'd flip it up or flip it down depending on whether it was on or off. Once an instruction was entered, you'd flick another switch and that instruction would be stored in memory. And then you'd go through the same process for the next instruction and on until all the instructions were input. Finally, when you had all the instructions, you'd flick another switch and then the program would run on the computer. And then when the results were done, you'd see a whole bunch of lights lighting up, indicating the 0 and 1, what the result of the computation was. We, of course, no longer write applications in zeros and ones. We no longer write them in assembly language, though I must say some people still do write in assembly language if they want to speed up the performance of their particular programs. We, of course, and most people today just write in a programming language. So which programming language do we use? There are hundreds of languages available at any one time. Only a few are popular. In this course, in this boot camps, we deal with C, C++, and Python. The thing about programming languages, if you learn to program in one, you pretty much can program in any language. They're all very similar. It's just the syntax of the programming language changes. That's kind of what I'm trying to demonstrate on this slide here. So in the first week, we looked at Python, which is considered a high-level language, which is, high-level languages they're easy to write your programs in, as opposed to low-level languages, which are a lot more difficult to write programs in. Last week, you were writing, you're doing more circle and drawing the results on a screen on day 2 of the exercise. You will not be doing that in this week in the C and C++ course. C and C++ are more low-level languages. They are much harder to write programs in. The development time of a program in C is a lot longer than something in Python. But the advantage of these low-level languages is performance. Low-level languages perform an awful lot better than high-level languages. So your C programs will kill your Python program in terms of performance. So I said it's faster. Just how much faster is a C program than a Python program? These results came out of a somewhat recent paper where they were showing how to, matrix multiply. They just wanted to show, if you wrote numerical operations in Python versus those same numerical operations in C, how much slower would your Python program be to your C program? And the result shown down here, basically, if you fully optimize, parallelize, and put in the right compile time switches and take advantage of the hardware, you will get a program that's over 60,000 times faster than a Python program. Why? Why is that? Ultimately, performance comes down to writing code that takes advantage of the computer hardware, and C and Fortran programmers are forced to write programs that follow the hardware. So let's look at the hardware. Ultimately, the desktop computer these days, they're pretty much all the same, whether it's a laptop or a desktop. You have a motherboard. Connected to the motherboard by typically some long ribbon is the hard drive. We have external slots for connecting monitors and keyboards. The brains, the sort of the bus, the highway of the computer is the motherboard. Attached to the motherboard, directly on the motherboard, is the CPU. The CPU is connected to all the devices through the motherboard, and it's also connected to the RAM, which sits on the motherboard. The CPU itself is made of multiple cores. Each of these cores is capable of running a computer program. The cores, they have their own level 1 and level 2 caches, and all the cores will share one level 3 cache. So the important thing to note about the hardware setup is that the cores only work on data in registers. If you want to add two numbers, those two numbers have to be brought into the registers of a core before the operation can proceed. So it's why you have to really understand the memory hierarchy of a computer to fully be able to utilize it. So this is the memory hierarchy of a modern computer. We show the cores. The cores have these registers. You'll hear about registers a lot in this course. The registers are where the data has to be before we can do any operations on the registers. These floating point operations can only work on data that exists in the registers. These registers exist on the core. Also on the core we have what are called level 1 and level 2 caches. All the cores share this level 3 cache. Attached to the cores via the motherboard is our RAM. And attached to the motherboard via this long plastic cable is our disk, our hard drives. Now to access data, if it's out on memory or if it's on disk, it takes an awful lot of time to bring that data into the registers so that the operation can be performed on them. So it's why when we're writing our programs, our C and Fortran programs, we're able to take advantage of the fact that we can curtail how our data is stored in memory. We can place it, we can optimize its placement if we cleverly write our programs, and we can cleverly take advantage of the level 1, level 2, and 3 caches if we know the cache policy of the core, and all the cache policy is typically the same. And for example, we'll see on day 3, knowing the cache policy, how we can greatly improve the performance of our programs. Again, C and Fortran programs, they run that much faster because basically they're taking advantage of this memory hierarchy, and that's something Python programmers have little control over. So the cache, for those of you who don't know, it's small, fast memory. It exists between the registers and the main memory. It keeps a copy of data in memory, but it's also hidden from the software. Your programs, when you write them, you can't actually tell the hardware what data to put into the caches. That's up to the hardware. But knowing it exists and knowing how it works, you can actually write faster programs. And caches work for two main reasons. One, idea of temporal locality. If you're using data, this dot product, chances are the program, some instructions down the road are going to be using that same variable. So if we want to keep it in the registers or keep it close to the registers, that's the idea of temporal locality. And the idea of spatial locality is we're using one piece of data in memory, the chances are we're going to be using the piece of data right beside it. That's the idea of spatial locality. So caches, they'll bring a chunk of data. What they do is they bring a chunk of data in all side by side. So when you start working on the data in the cache, all the data will be there. And we can't program it. The operating system has no control over it. But knowing it's there, we can write better programs. Knowing the cache policy, we can write faster programs. And that's what we'll do on day 3. So now a little break. We're going to look at what the actual program looks like. When you write an application, it's when the application is then brought into memory, the application, the program address space expands greatly. The application itself takes up what's called as text data. As it starts running, there's additional data that's created for it. And then while it's running, every time you call a function, memory is being allocated from the stack, from the program's memory. And every time you look for data, as you see when you every time you create an array or a matrix, that data is actually coming from this heap. So again, when you call a function, it enlarges the stack. What's put on the stack is all the function variables. Like for example, when you did Fibonacci, it would recursively call itself. And each time it called itself, basically, the stack would grow. The variables for that function at that particular time is put in the stack. And then when the function goes away, the stack reduces. Heap, that's again where we're going to be getting our memory for our vectors and our matrices. And they're all coming from the heap. And the program runs out when there's just no more memory available. These days it's pretty hard to run out of program address space because we have a 128 terabyte address range, which is huge. Problem is with this address, it doesn't all fit in RAM. For example, we got a 32 gigabyte RAM, and you've got a 128 terabyte address range. The program is not going to squeeze into our little itty bitty RAM. So what the operating system does is it breaks the program into pages and brings pages in and out from disk as it needs it. And when a page fault occurs, your program dies basically. It's basically the program is kicked out of the processor and it will sit there waiting until the data has been brought into RAM, which will kill the performance of your computer. So when you're writing these programs, you want to minimize page faults. To minimize page faults, you optimize where you place the data in memory.